So a couple of people have emailed me about the midterm projects saying that how do you both access one database? Surprisingly few of you have emailed me about that, which leads me to believe that your week off was very relaxing. Probably more relaxing than it should have been. But anyway, if two users want to both access the same database, then just send me the name of the database and the user, and I will just change the permission right away. You can do it on Discord or on email, and I can change permissions. I have not yet figured out how to give you that permission individually, but if I do, I'll let you know, and if you do, let me know. Okay, you can create as many databases as you want. They just have to start with your ID number. So AB1234 CD underscore, and then whatever you want, you should be able to create. Next week is going to be presentation days on the midterm project. Obviously, you've had 2 weeks plus to work on it, so I'm expecting some good work. First, your clients will go first. You'll have 30 seconds to say, this is what we wanted. These were the requirements we gave them. And then the developers will have maximum of 2 minutes on their design decisions and implementation. So if your client said, we want an app that cures cancer, you can talk about how, well, we were able to, do X, Y, and Z, but we were not able to cure cancer in 2 weeks. Then you're going to demonstrate your app, maximum 3 minutes, and I will cut you off because with this many people, we don't want to go beyond too many days. We will almost 100% have to go to Thursday as well, but I'm guessing Thursday would be very short. So if everybody can stick to 5 minutes, we may not have to go to Thursday. It's up to you. The midterm will be posted next Thursday at 1 p.m. So after the class, it will automatically be posted, and you will have 1 week to do it. It will include everything up to this point. So I'm gonna start talking about NoSQL and MongoDB today. MongoDB and NoSQL will not be on the midterm, but it will be on the final. So everything up to this point will be on the midterm. It'll be similar to that first homework where there were like 8 questions and you had to explain things. So the feedback, a lot of the feedback from that was that you did not explain things thoroughly enough to convince me that you knew what you were talking about, right? So if I ask you, what the difference between SQLite and MySQL is, and you say one is a single file and one is, a big server, and that's all you say, okay, that's one thing that didn't really convince me that you know the differences between the two. So again, it's open book. You can use whatever resources you want except for each other. So don't work together on it, and cite your sources. So as I've mentioned before, Wikipedia is actually a reasonable resource for database stuff because only database nerds read Wikipedia about databases. So it's not super controversial, but there are a lot of other resources out there that you can use. And then it will be due the following Thursday at midnight, and I'm going to lock the submissions at midnight. So in D2L, it will automatically stop accepting submissions at midnight. You can, this is going to shock you, so you probably want to sit down, submit early. So you can actually do it before it's due. I know, crazy talk, but it's happened. It happened once, and the person did not die, so. Surprise! Your app must include at least 2 types of users. So this is one thing that we were going to talk about last Thursday. So I scaled it down a little bit because we didn't have class. But you must have at least 2 types of users in your app. So something like a library customer and a librarian, right? And at least one type of those users has to log in with a password. So I'm leaving it really open-ended on purpose. Does every user need to have a username and password? Are you just going to have one admin password that everybody shares? Are you going to limit it in the database to what specific users can do with actual database users? That is not required, but if you want to try that, to learn what that is like, you are welcome to. But this is the minimum requirement, is you have to have at least 2 types of users. They don't have to be called this. Those are just examples. And at least one type of user has to use a password or user. If you want to share one password among all your librarians and be really insecure, that is your choice. Any questions on that little wrinkle? All right. So just for reference, last Thursday, the clients had to come up with an extra feature for you to add that added another table to your database, because that's what clients always do. So that might happen in the final. FYI. All right, so we're going to start on NoSQL today. This does not mean what you think it means. It just means not only SQL. So it's not like the opposite of MySQL. It just means, hey, there's lots of other ways to think about data. And as you can see, this is just a random bunch of pictures of not MySQL databases. Some of them are similar to MySQL. Some of them are very not similar to MySQL. The one that we are going to focus most on is MongoDB for various reasons, not the least of which is because it is probably the most widely used NoSQL database. It uses the type of data storage that is most commonly used. So we'll get to that. So first thing we're going to do is run a little experiment. We're going to get into groups of 4, and 2 people are going to be database servers. So Brian and I are going to be the database servers, right? And we're going to need a sheet of paper and a pen, and you're going to need to write down some data. The data is going to be really simple. Okay, it's going to be like a name, Alice, and how many friends she has. 5. 10, 15, whatever. Or a population, Toronto, and, a city, Toronto, and its population, I don't know what it's at, 5 million, right? The other 2 people are going to be the database users. So Melissa and Lauren are going to tell us to update our database. They're going to add information to our database, and they're going to ask what the information currently is. Brian and I have to both write down what they tell us, add Toronto 5 million, update Toronto 10 million, update Toronto 10 million, and try to keep it synchronized because we are both the same database. We're just 2 different servers of the same database. So we are trying to keep our data consistent and updated from what Melissa and Lauren are telling us. And they can talk to either one of us at any time and update any data at any time. And you can update it any way you want, like a database. You can say, add 5 friends to Alice, add 1 million to population of Toronto, subtract 5 friends from Alice, add 5 friends to Bob, whatever. So you need to, the 2 databases need to try to keep their data consistent, so we can look at each other's sheets and try to keep them updated. And the users just keep talking. Don't wait for the database to finish. right? Be rude. This is just an exercise. I know we're all Minnesotan and we want to wait for everybody to finish and be polite, but this is your time to be from Wisconsin. I'm just kidding. So we are going to really try to overload the databases. That's kind of the point of this exercise. So I'm just going to make groups of 4 because that'll be easier. So 4. All right, bring it back, ladies and gentlemen. Bring it back. All right, so what are some of the problems that the servers had? Signal strength. Speed. Space. Oh, really? You ran out of paper? Yeah. Yeah. So there was the speed was kind of the number one. You couldn't write as fast as they were talking, right? Yeah. What about keeping synchronized? What were the problems there? Couldn't hear both. Okay, yeah. Reading from multiple sources. Yes. What are some of the other problems? Mishearing. Oh, mishearing. Ah. Mishearing. Yep.
Wrapping concurrency at the same time.
How do you mean?
In a group of 4, like 2 people are talking.
Yep.
Saying 2 different things at the same time.
Oh, so like updating the same things at the same time. Yep. Updating same, I just call it row with different info at once.
Multitasking.
How do you mean?
He's telling me one thing and I got to check with her to see if she has
Sure, multitasking.
Probably another word for that, but
Nope, that's totally fine, yeah. Conflicting information.
Lack of specificity.
How do you mean?
Well, if I was actually SQLite, I would have thrown an error a couple times.
So these guys kind of started doing something like that.
Yeah.
Where
Like,
they were like, stop!
we've been talking about quantities of ice cream.
Yeah.
9 kinds of ice cream. And they said chocolate, vanilla, and then they said 50 raspberries. And I was like, do you want raspberry ice cream
Right.
or raspberry?
Like, what does that even mean? Yeah.
Just crashed the whole system.
Yeah. All right, so this is, yeah, those are really, really important problems. So what did you guys do, right? So if user 1 said to server 1, Alice has 10 friends, and user 2 said to server 2, Alice has 15 friends, what did you guys do? What did the servers do when you had conflicting information?
Wait
Clear.
to synchronize.
But how did you synchronize? Who decided what was the right answer?
The louder person.
The louder person? Got it last? Okay, that's interesting. So if this happened first and this happened second, then you overwrote that with this.
yes,
Interesting. Okay.
she talked faster than him, so
Yeah.
she's
So
to that effect.
speed versus volume. Okay. I'm going to update my database loudly. I'm really pressing hard. I mean it.
The most clicking all caps.
Yeah, yeah. Okay, so that's a big problem. So here's another common problem. Say Alice starts with 20 friends, and user 1 says Alice now has 15 friends, and user 2 at the same time says remove 5 friends from Alice. Does that mean Alice has 15 friends or 10 friends? Right? Right? So these are really hard problems. Right? These are the problems that you are having are the problems that databases have, right? Because if I have a server in New York and I have a server in Los Angeles and I have lots of people using them, my website, right? How do I know how to synchronize them, how to update them, right? So MySQL is the standard, right? Or not MySQL, but SQL, our relational database, what MySQL is the standard for very, very good reasons and has been around for more than 50 years now for very good reasons. So it's something called ACID. And you might have heard of this, I don't know if you heard of this in your previous database course, but the principle is called ACID. And the first part of it is called atomicity. And it means that something that is a transaction is what we used to think of as an atom. You cannot break it apart, right? So say I'm a bank and Melissa is sending Lauren $50. So if I am debiting $50 from Melissa's account and crediting $50 to Lauren's account, that's one transaction. I don't want to be able, during the debit, if the power goes off, right? Suddenly Melissa doesn't have 50, or has 50 fewer bucks, but Lauren never got the other 50. That's a bad state for the database, right? It's inconsistent. It's the transaction was broken in half. We do not want to have that. So they designed MySQL that any transaction is atomic. If the power goes off in the middle of that transaction, it's like it never happened. The whole thing never happened. And this can be not just like a debit credit, but really complicated. You can imagine a really complicated transaction that hits a lot of different tables, right? Did you have a question?
Well, I just kind of have a comment.
Yes.
So would that be something like, almost like with Git, where you stage something in the whole transaction and then you submit the entire transaction at once?
That is one way of solving the problem, yes. So we'll get there, yes. But the first part of ACID, I just want you to understand that a complete transaction either happens or it doesn't happen in MySQL. That's really important for a relational database. Consistency means it's always in a valid state. So we haven't done much of this, constraints, cascades, and triggers, and we're not really going to, but you can imagine an example where when I add an employee to a database, right, it triggers a whole bunch of stuff in the database, right? I have to add vacation time in the vacation table. I have to add blah, 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 number of hours, taxes, Social Security. All these other transactions start happening that are triggered by my first transaction that is just adding a new employee. So a trigger is a way, literally, of triggering other transactions to take place when something happens, right? You add a new sale, it triggers a profit and loss calculation for the week or something like that, right? There's all these different things. Constraints we dealt with a little bit, key constraints. But these are things that happen like to make sure the database is consistent. And again, if the power goes off in the middle of these, as soon as I enter the employee and before it has time to add their vacation and their taxes and Social Security, the whole thing is rolled back. It's like I never entered the employee in the first place. So that's what consistency means. If the database is left in a bad or inconsistent state, then the transaction is rolled back. It never happened. So isolation's a little bit trickier, and this is kind of what you guys were talking about when you were saying stop, right? Because if two people try to update the same thing at the same time, right? Alice has 5 more friends or Alice has 3 fewer friends, right? If I do those at the same time, Alice plus 5 and Alice minus 3, then I'm going to get the same answer, right? I'll get plus 2, right? Same thing as if I did it sequentially. But if I say Alice had 20, now Alice has 15, and somebody else says Alice minus 5, that was the example where I don't know if they meant 15 or 10. So what does it mean if I'm doing the transactions sequentially, one after the other, or if I do them at the same time, they have to have the same answer. So what will happen is I will have to lock the table so that only one thing happens at a time. So I can lock a row, I can lock a table, I can lock an entire database, but depending on how important it is that my data is, like in a bank, they will lock an entire table, right? Because they don't want a debit and a credit to not happen because somebody else is trying to do a debit and a credit on the same account at the same time. So while you are doing one transaction, it will lock the table, but that means you can't do concurrency. It means somebody else can't update that same row in that same table at the same time. If you don't care, if it's like Twitter, right? You don't really care whether somebody's tweet gets garbled, right? Then you can allow people to edit things at the same time, and you just carry on. This is more of isolation is about how important is it to you that everything that happens at the same time looks the same as if it happened in the specific order. You have to have the ability to lock various levels of your database, to isolate various levels of your database. And then the last part of ACID is durability. And that goes to, I don't remember who said, kind of like the staging, right? Where once the transaction is confirmed back to the user, it means it has been written to non-volatile memory. So if the power goes off, when I turn the power back on, that transaction will still have been executed, right? If I subtract 10 million people from New York and shut off the power right away, and I turn the power back on, if I got confirmation of that transaction, I'm expecting 10 million fewer people in New York. Whether I'm Thanos or not, I guess. But durability means once I'm told my transaction is done, I know it's done forever. Whether the power goes on or off, or the server burns down or whatever, there is a record of it being done and complete. Because as you can imagine, with databases with millions of concurrent users, you don't want to be writing to disk every time, right? So you have to do a lot of things to make sure that transactions are permanent every time you tell someone that it's permanent, that it's done. So this is the basis of a relational database system, that all of these things exist in the database. You have to have the ability to have indivisible transactions, all or nothing, that the database is always in a valid state, right? Remember, this is once a transaction is complete, and I'm told my transaction is complete, that the database is in a consistent state. It never does half of it and then lets me start something new. Isolation, same thing. It never lets two things happen at the same time that would be different if I did them in sequential order. And finally, when I'm told something is done, it's done forever. So that is why relational databases are so prevalent, is because they err on the side of safety and security. Yeah, I don't need to go through this example. CAP theory is a theory about distributed systems. So this is a little bit like what we were just doing in the example, where you have two database servers, and you have a network partition. So it's when I say pick two, I mean pick this one and one of these others, right? You can either make sure that these two databases are always in sync, like saying, stop! Don't allow anybody to update. We are talking to each other, making ourselves consistent, and literally blocking all transactions until we are consistent. Or we can be available and not say stop and just be like, yeah, we're trying to be consistent. Not doing a great job at it because you guys are talking so much. But you can only have one of these, consistency or availability. I can be available for you to send me stuff all the time, or sometimes I have to say, wait a minute, we have to synchronize to make sure that we are up to date. And it's like a scale, right? It's not a 1 or 0. It's like how important is it to you? Again, with Twitter, right? Do I care if a Twitter user in London has slightly different tweets than a Twitter user in Sydney? No, I don't care. The consistency is not important. But the availability is important. If Twitter goes down, I am losing money. If the Twitter database has to stop so that London and New York and Sydney can all synchronize with each other, I'm losing money. So it's much more important for Twitter to have availability than consistency. But for a bank, right, I would rather say, stop, we need to make sure our debits and credits are right. You can wait with your transaction for a few seconds rather than have bad transaction data. So what does it mean if we don't use ACID? So if you remember that rap that I played for you, one of the lines in the song was ACID versus base. What's the difference for my database? Do you want me to sing the whole rap for you again? Yeah? Okay. Maybe later. I'll be here all week. But what it means is basic availability. So there is no guarantee of availability. Soft state means I am going to take transactions and not necessarily do them right away. And the same thing with eventually consistent means when Brian and I get around to it, you know, when things calm down a bit, you gotta stop talking so much, then we'll talk to each other and we'll make sure we're consistent. And we'll have rules about how we do that, right? Who sent me an update first, like you guys were saying? Is it time-based? Is it volume-based? Is it, you know, we'll have some kind of rules about how we decide what transactions take precedence. But we're not worried about doing it right away and stopping everybody else from updating. So base is a little more laid back. And again, which one is better? It depends. The motto for this course, right? We're going to get into use cases a little bit later for each kind, but there are a bunch of different kinds of NoSQL databases. These are the most common ones. So these, React and Amazon S3, are a key value store. So they are very, very, very fast because you cannot update. You can only insert and delete and read, right? So you basically say, I have a key. It's like a dictionary. I have a key, Romania, and I have a bunch of data associated with that key. It doesn't matter what that data is. There's no column type. It's just data. So this is like amazingly brilliantly fast if you just have one key and a bunch of data, right? So if you want to know all the information about the people in this room and you only ever look them up by first name, this would be a great way to do it, right? Because this key is like a primary key. The data structure in the background makes searching for this extremely fast, right? And then, but you can't search by like zip code. It doesn't work that way. You can only search by the key, and you can only get the data that's in the value. So that's a key value pair. And you can't update. You can't, if I want to update Romania, I have to delete Romania and put in a new Romania, which is actually not that bad, right, for this kind of database. I want to skip MongoDB. I should have reorganized this because that's what we're going to. So column-based store is, think about a relational database, but rotated. So in a relational database, each row is kind of its own thing, right? It's like one person, one textbook, one class. Yes? Yeah, I'm recording. So each one of these is kind of one entity in your database. That's what we're used to thinking of. In a column-based store, it's rotated the other way. So you have a column, employee ID, and it's associated with a row ID, but it's associated this way. So you have on disk all the employee IDs associated with their row IDs, with their primary key. The next entity is the concept of a last name, and all of those are stored with their row ID. And then their first name is stored with their row ID. So each column is sorted, right? So sorted alphabetically or by number, and then stored with their row ID. So this obviously has very specific use cases, and we're not going to go into it. I just want you to be aware of it. Right? There are different ways of organizing data. It's not intuitive, but it is much better for certain use cases. So it is much easier to find, well, I don't know how much I want to get into this because I don't want to confuse you guys too much. Each row is going to have a unique key. So a row ID, just like our primary keys. But each column is going to have its name, its value, and its timestamp associated with it. So I still like that first slide the best. And that doesn't really explain well. Yeah, it does. The nice thing about the column-based store is that I don't have to have all the same data. It's not a perfect rectangular table like MySQL where each row has exactly the same columns. It is easier to have one user with individual columns based on that user. I feel like I'm saying too much. Again, the primary goal of this is understanding that there are different ways to store data. So graph-based stores don't store according to a primary key at all. The way you store data in a graph-based store is you store like the ID, the name, the age, and then you store their relationships. So you don't have, again, a rectangular box of rows. What you have is a bunch of entities or nodes and relationships between those nodes. So, for example, they're used for like recommendation engines. So if you have something like Netflix, you can store all the movies as nodes and all the users as nodes, and then you can store John likes these 10 movies, all these relationships to these different movies. And this movie is related to that one because these are all different genres of movies. So instead of trying to keep a list of all the movies that I like and all the list of other movies that are connected to this movie, right, in like a rectangular database, which doesn't really fit the data model, you have individual nodes of users and movies, and then you just store the relationships between them. And that way, if I want to say, what movies does John like, it's really easy for me just to find the relationships between, or Alice and all the movies that Alice likes. And if I want to see if Bob likes 20 movies and Alice likes 10 of the same movies, it's really easy for me to say, hey, Alice, here's 10 more movies you would like, because Bob has the same relationships to those movies. Bob has a lot of similar relationships as you do to movies. Here's 10 more relationships that Bob has that you don't. So again, specific use cases. This is also good for like mapping Google Maps, obviously. If you have places you need to get to and the distances between them and you're trying to figure out how to get from one place to another, it is much easier to follow relationship paths than it is to try and do searches through a table. Yes?
So could that be like Amazon when you buy something, it'll recommend things to other people who bought that?
Exactly. Yeah. I mean, I don't know for a fact that they use a graph database for that. There's obviously many different ways to do it, but that would be one way that they could do it, yeah. Because they will have all the products you've ever bought, all the products I've ever bought, and if they overlap by a certain amount, then they'll tell me, hey, I should buy some of the stuff that you bought, and vice versa. So unfortunately, it is very hard to debug this, because if you get some of these relationships wrong, it's very difficult to see where and how and why. The one nice thing about RDBMSs like MySQL is that when you look at a table, it's really intuitive, right? Like you just understand what's going on. And if there's something wrong in it, you can just kind of see it right there. If there's a phone number in the address field, you're like, that looks wrong to me. Whereas with this, right, if you have relationships like going the wrong way or in the wrong place, it's really hard to figure that out. It's really hard to debug. But anyway, so another type of database that is not RDMS MySQL. So the last kind that I want to talk about today is MongoDB. And I don't remember what this video is, so risky click of the day.
Another song about MongoDB.
How about some volume?
Rests on the fact that it's a document database. When discussing MongoDB data models, queries to MongoDB, and data stored in MongoDB, we use JSON or JavaScript object notation.
Has anybody ever heard of that before? Okay, excellent.
This JSON document provides an example that illustrates the type of data MongoDB stores as a single record. Important advantages of this design are that development teams can design data models to support common data access patterns. For example, a team building a news website can design their data model so that the most frequently viewed pages may require only a single query to the database, and can do this in an elegant way that is fully supported by MongoDB. In this example, we're combining copy, author info, tags, and comments to enable rendering a news article with a single database query. Contrast this with a relational design, which would probably require several joins across tables, or an ugly means of storing multiple values in single table fields. Since MongoDB data models are not predicated on joining data from multiple tables together, it's much easier to distribute or shard data across multiple servers. This means in MongoDB, you have a wide variety of options when considering database deployments, from many inexpensive commodity machines to a few larger, more powerful servers. MongoDB natively supports scaling out through its sharding feature, and does so in a way that is abstracted away from application logic. So developers can build their application in a way that is agnostic about the deployment model used. Whether a single node, or a few nodes, or hundreds of nodes are used, makes no difference from the perspective of the application. In contrast, since joins and multi-table transactions are difficult to do in parallel.
So what he's saying, let me just go back a second. And again, we're going to talk more about this later in the class. But what he's saying is because, right, you've modeled your data inside your database to match the way you're using it, rather than the way you're thinking about your data. You can have, say you have 1 million articles in your newspaper database. You can put 1,000 of them on 1,000 little computers each, and you'll have 1 million across the 1,000 little computers. It doesn't matter because you're not joining tables across those 1,000 computers, right? You're only ever going to look at one article which already has all the information you need in that one, right? In this one document. All the information you need is here. You don't have to join anything else. So there's no chance that one table's on one server and another table's on another server, and you have to somehow combine them over the network with a really slow join, because everything is in one document. So if you have 1,000 servers and 1,000 documents on each server, you're still only ever going to have to hit one server to get that document. So you can just keep adding more and more commodity hardware. Right? Like you can just go to Best Buy and buy another server and buy another server if you run out of space, and just put more and more documents on your servers. Whereas with MySQL, what he's saying is you can't do that, right? Because say you have 50 tables, right? As they fill up, how do you can't just buy another server and put like one of those tables on that server. It would slow everything down because you'd have to join across the network for every query. The only way, well, until very recently and still mostly, lots of asterisks, the only way you could make a SQL server hold more data is by buying a bigger server. Right? Because you need to have all those tables in the same place. Otherwise, you're going to kill yourself with performance.
Makes no difference from the perspective of the application. In contrast, since joins and multi-table transactions are difficult to do in parallel, for a relational system, your best option is usually scaling up, acquiring
And, right, 1,000 people can all access those 1,000 servers at the same time with 0 performance hit. They can update, they can select, they can delete, doesn't matter, because they're the only ones using them.
Increasingly expensive hardware so that your data can be served from a single server. While not always true, multi-table joins and transactions are typically not missed in a MongoDB database because the schema design capabilities support models that require atomic reads and writes only to individual documents. So, in summary, MongoDB enables application developers to design data models that make sense for their applications. That is, those that efficiently support common data access patterns. As we'll see as we move through this course, MongoDB is designed to support agile software engineering practices and meet the scalability.
As soon as you said agile, you lost me. So this is the example from that video. I just took a screenshot. But basically, there's some huge advantages to designing your database based on how you're going to use the data, and some disadvantages, right? Some of the advantages, you can actually add random fields at will, right? So say you never had comments. Say like you thought that your newspaper was only going to be you and your best friend, and then all of a sudden it blew up and it's really popular and everybody wants to add comments to your articles. You can just add them. You don't have to add another table. You don't have to add rows or columns or anything. You just start adding comments to your documents. It just works. You just do it. And your old articles don't have any comments, and that's fine. MongoDB doesn't care, right? So you can just add random fields. If one of your articles needs to have a special field on it, you just add it. MongoDB doesn't care. It's just a document that is formatted a very specific way. And then, so if you remember the key value pair that I talked about briefly, which was this, very fast, very expansible, but no atomicity, right? This one you can actually query on subfields. So in the key value pair, you could not query for anything inside here. You couldn't say, give me zip code 3011. It just doesn't work that way in order to maintain its speed. Whereas this one, you can. You can say, find author Bob Walker. It's not fast, but you can. All right, so I think, oh yeah, so here's an example, an article in content management system, right, with author and tag. So this is what we might do, right, in our RDMS and MySQL, you would have all these different tables, and it's just to contrast how it would be in a document-based store, right, where it's all together in one. So, but you don't have ACID with this, right? So if you don't care about that, then it's not a big deal. It depends, right? It depends on what your priorities are. So we are going to get very deep into MongoDB for the rest of the course, but I feel like that is a good place to stop for now.